my talk is on estimation of variance components in mixed model corresponding to block design. I would like to present some results concerning quadratic estimation, where the usual assumption on normality of data are less. So let us consider a general mixed model in which the observed vector y has the following structure. X and ui are known matrices, beta is the vector of fixed parameters, and psi I are vectors of a random vector, but all components of psi I for fixed I has the same variance, say sigma square I. And the components are also assumed to be uncorrelated. In such a case, we have the expectation of y equal to x beta, and the structure of variance-covariance matrix is linear combination of known matrices with unknown parameter sigma I squared. The problem is how to estimate these parameters, and usually the class of quadratic estimators, which are invariant with respect to such translations, I use. Very known popular class of estimators are so-called mean Q, proposed by Rao. Here we have the explicit formula for mean Q. There are linear combination of such a matrix, where V is ui prime, and V alpha is linear combination of Vi. Alpha is some, how to say, prior value corresponding to prior information about sigma. Lambda is such chosen that the estimator is unbiased for this function. And CV in 1970 and 1971 proved that if Y is normal distributed, and if the space V defined here is a quadratic subspace, it means that if A belongs to V, that also A square belongs to V, then there exists, then for each invariantly estimable function, there exists the uniformly minimum variance invariant quadratic unbiased estimators, and this estimators coincides with mean Qs. But normality is very important assumption here. Anderson, Henderson, Kukesheim, and Serre in 1984, in the paper published in Mathematische Operationsforschung, proved that we can drop the assumption on normality of Y, and if we take so-called balance data, balance means that the matrices X and Ui are Kronecker products of identity matrix and the vector of units, then mean Q is still the uniformly best under arbitrary kurtosis. No, this assumption on balance data is rather strong, and there are only sufficient conditions for mean Q to have such a nice problem. I would like to give necessary and sufficient condition, but for some special model, not for O1, model corresponding to block design. So we have 10 experimental units representing V treatments, which are arranged in B blocks according to some incidence matrix N, notation unknown. And we assume the following model for this data. Y equal d prime beta plus delta prime gamma plus vector of errors, but we assume that only beta is fixed. The vector gamma of treatment effects are random. The assumption that beta is fixed and gamma is random is some kind of convention. Of course, we can also consider the case that gamma is fixed and beta is random, and consider so-called dual block design. putting transformation of n instead of n. It doesn't matter from theoretical point of view. Additionally, we assume that the force moment of gamma A and EA are the same for all components gamma and all components E. There is the only assumption on the distribution of y. And there is notation of them. The problem of estimation of variance components without assumption on normality has been originally considered by Xu in 1938 for the model with one variance component only. And also intensively studied by Drygas and Szydlicka, Drygas and Puppet and Puppesheim. A lot of interesting theory concerning estimation without normality also contained in the book of Rao and Kleffer, where model with several variance components are considered. From this theory contained in this book, it follows the following lemma follows. If you have the model corresponding to block design, then for each invariantly estimable function, mean Q is the uniformly best under arbitrary kurtosis if and only if V is a quadratic subspace and some additional four condition code. The notation are explained here. C is the informative matrix, M is the projector of the null space of D. I use here capital R, sometimes R delta is used. But it is diagonal matrix with diagonal elements equal to treatment replications, and K is diagonal matrix with block sizes. So the problem is to express this condition in terms of the incidence matrix N or in matrix C. It would be interesting in practical proof. So the basic for further consideration is lemma. The following lemma, proved by Baxalari by myself in the paper accepted for publication in JSP, Journal Statistical Primitive Inference, where the necessary and sufficient condition for V to be quadratic subspace are given in terms of the matrix C and the incidence matrix N. V is quadratic subspace if and only if for some alpha C has the following structure, or when V is greater than 2 and the block sizes are greater than 1, the incidence matrix is isomorphic to that one. It means that under normality, such a block assures the existence of the uniformly best estimators for variance components, for each estimator function of variance component. So let me say that such a block in the analysis of fixed model I call it variance balance. So here, if you are interested in estimation of variance components, I think that this term has no any justification. That's why I will not use it. The assumption that V is greater than 2 follows from the structure of N. It's not restricted. But this assumption is also very formal because in invariant estimation of variance components, if you consider block of size 1, then observations are dropped, are removed by invariance principle. So it doesn't matter. You can also add some blocks of size 1, but it doesn't matter for estimation. C is the same. The matrix C is the same. It is also interesting that here C has the only positive eigenvalue, but in this case, C has the following structure, and we have 2 positive eigenvalues. And my problem is, which of this block design satisfy this 4 condition that I mentioned earlier? Let me recall on the next second. I don't know what happened. Orange? Oh, I'm sorry. How to specify block design which satisfy this condition and in addition these 4 conditions in terms of N or C. And the theorem is as follows. Oh, just a moment. Let me say that here I restrict my consideration to connected block design. It means to design for which rank C is equal to V minus 1, but in fact it doesn't matter. It's very easy to extend this result on disconnected block design too. And now the main theorem. In the model corresponding to connected block design, is the block size greater than 1. For each invariant estimatable function, mean Q is the uniformly best under arbitrary kurtosis if and only if corresponding design is equal block size, all positive elements of the incidence matrix are the same. Of course, we can have 0. And the matrix C satisfies the same condition as earlier. So, since block have to be equal block size, and the matrix C has the following form, it follows immediately that the block have to be also equi-replicated. It means that the only unequal replicated block design that assures the existence of the uniformly best estimators without assumption of normality is that one. So it means that it's really very interesting design with the smallest number of observations, which has very nice problem. Of course, there are very easy to find a lot of examples of design satisfying this condition. One of them is here. There is an example of the matrix. Incidence matrix with diagonal elements equal to 0 and off-diagonal elements all equal to 1. The matrix C has the following form. Let me say that this example do not satisfy the conditions of balancedness proposed by Anderson, Henderson, Hookersheim, and Shah. This theorem can be very easily extended for the case of disconnected block design. In the model corresponding to disconnected block design, disconnectedness is defined here. It means that rank of C is equal to V minus Q minus 1. If Q is 0, then we have connected design, so let us assume that Q is positive. Then, in the model corresponding to this design, mean Q is the uniformly best if and only if N is isomorphic to quasi-diagonal matrix. So this has been mentioned by Professor Czaliński earlier that it is possible to do. All of sub-designs are connected. All positive entries are the same, and the matrices C, in fact, has the following form. It is important that alpha is common value for each subblock designs. Or the ratio V over Q plus 1 is the integer. It is also necessary for structure of this matrix N. And N is the Kronecker product of such matrix. The characterization of this plot is very similar as in connected situation. It means that there is design not replicated. So, and at the end of my lecture, let me present some details concerning the basic paper that I use to obtain these results. This mentioned paper written by Anderson, Henderson, Hookersheim, and Shah. The paper of Barcelona, Robert, and myself, and the book of our Clever, the interesting theory. That's all with you for the research.
Thank you so much. Any questions at this paper?
Yes, at the beginning of your talk, you mentioned that this model, although considering block effects as constant and treatment effects as random, can be also treated in the other way, right? By some duality. Well, it seems to me that this would only be true if by randomization you get your blocks chosen from an infinite number of blocks, and if the units which form blocks have also been chosen from an infinite blocks. I mean blocks of unrestricted number of elements. Because if you perform the usual randomization and base your model on that, then the block elements, I mean the variables which represent block effects, would be correlated.
Well, thank you for your remark. I'm not an expert in block design, so I believe that you are completely right. Anyway, there exists such a model. It is not so artificial.
Well, exists in the literature.
Yeah, no, but I think that the idea was that what is actually considered is two-way cross-classification without interaction with one factor random and the one fixed.
Well,
but of course, these block designs were used because of convention. So it is not necessarily starting position is not necessarily any block experiment. It's just, I think the starting position here is a model. Two-way cross, no interaction. One factor random, one fixed. That's the starting point. But of course, in the particular context of block design, so that's
If there are no further questions, okay, that's a question.
I'm intrigued by the second class of designs where you have the identity matrix on the one on the bottom. The first condition is very closely related to what happens with balanced incomplete block designs. So the first condition is somewhat intuitively clear to me. But what does the second class of design mean? Do you have any intuitive explanation of why this class of design performs so well from this type of explanation?
Oh yes, okay. The problem is in the first condition. It means when V is quadratic subspace. It's very closely related to this condition. So let me explain more details concerning the invariant estimation of variance component, then it would be clear, I think. But I have to use the properties. So if you have a model, a general model with two variance components, E plus I, then you can choose such a matrix R and assume that the rank of X is equal to n minus p set. Then you can choose a matrix B having the following property: B prime is identity and B prime B is equal to orthogonal projection on O. That's okay. Then you can use the maximal invariant statistic E, and the model for T is as follows. The expectation is 0, and the variance covariance matrix has the structure sigma 1 B prime plus sigma 2 B. And everything depends on the algebraic properties of these matrices. So B prime, say B, has a spectral decomposition, say alpha of B. And the last eigenvalue can be 0 or not. If it is so V is quadratic subspaces if and only if H is less or equal to 2. And if alpha H is equal to 0, then we have only one positive eigenvalue for V. If alpha H is positive, then we can choose two positive eigenvalues for V. And this is this case of the block design. In the second case, we have the situation that eigenvalue, the last eigenvalue of W is also positive.
May I make a comment?
Yeah.
Well, in the literature, this class of designs is very well described. It is called simple partially efficiency balanced designs.
Thank you for the remark.
Well, we'd like to thank the speakers for the presentation.